So just a reminder from last time, we discussed how this will be implemented inside a computer. We're talking about news, and we said there's no single instruction to do this kind of thing if we want to assign initial values. There is an add that's repurposed to also become a move, because we know that our 0 is always 0, right? You remember this from last time. The other thing with this, so this will get translated into 3 steps, actually 3 instructions. So that's a monolithic operation. As we discussed last time, there's no way to do any kind of constant we wish we could do. First of all registers up to 32 bits, so regardless, there is a limit over there, 32 bits. Furthermore, there is a limit by the instruction itself that's 16 bits, and it's a signed number. So if you want to do anything, any number that does not fit in 16 bits as signed representation, you have to do something else. And we discussed why this is the case. It has to do with the vocabulary we use to talk to the computer. It's a binary thingy. It's a 32 thing. Every instruction is 32 bits. When you think about what you have to do to express an add I, you have to say, I am an add I. This is done by the lower 6 bits. You need to say who's the destination and who's the source. And there are 32 registers, 5 bits each. And then whatever is left over is what's available to you to say what the immediate is. That's why there are 16 bits. And by convention, this is for this machine, this is a signed number. So we discussed last time, if we want now to load a number that's more than 16 bits, requires more than 16 bits, you have to synthesize that using a bunch of operations. And we said that the trick there is to view this conceptually as 2 parts, the lower part, lower 16 bits, and the upper part. Again, this is stuff we've done last time. And I gave you one sequence of operations. There is a move high instruction, which loads the upper half into the upper part of the register, zeroing out the lower bits. Okay, this part. And then there's ORI that treats the register as a collection of 32 individual bits. It takes another constant and does bitwise or Boolean OR operations. Everybody okay with this? This is just review from last time. Any questions about this? Okay, I'll take the blank stares as, okay, let's move on. I don't blame you, this is so exciting for me too. Okay, so this is the full sequence of code that allows us to load the operations in. Okay, so we have 2 instructions to do one of the constants, another 2 set of operations, instructions to do the second set of constants, the second constant, sorry, and we're done, then we put the add underneath and we're done. That's the why, that's what this will get translated to. So you have what looks on a piece of paper like 1 operation gets translated into 5 underneath. Okay, there are 4 for creating the constants and the 1 add that I'm not showing on this slide. Okay. Now, because people are nice, sometimes they want to provide you with convenience. This is the point where we stopped last time. We said that we're going to be writing programs in textual representation with characters, and there's going to be a nice tool that takes that and converts those into the binary form that the computer understands, because it has to be translated into bits. So it will translate every textual representation of an instruction into a sequence of bits, blah, 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 blah. So in that tool, in the language that this tool uses, which is called assembly, that's the typical name that people use. It's a textual representation of machine instructions. There are some pseudo instructions. These are not instructions that exist. These are facilities that the tool provides to make our life supposedly easier. There is move I, which takes a register and a constant that is a signed constant of up to 16 bits. This, I think, gets translated into an add. It doesn't matter what it gets translated to. The effect that you need to understand as a program is that you take that number and it gets converted to the 32-bit equivalent representation inside the register Rx. Rx can be anywhere between 0 to 31. But 0 always ignores you. There is move UI, the U stands for unsigned. In this case, it will take a 16-bit unsigned immediate. Okay, forget about how this is actually implemented. That's what you need to know as a programmer. And it will convert it to its equivalent representation in 32 bits. Okay, so it will 0 extend. The first one signs extend. The second one 0 extends. Finally, and this is the most one that you're probably going to be using a lot of times, there's another one, horrible name. It's called movie A. I'll explain why I think it's a horrible name, but I'll give them some credit to coming up with that name. This is something that takes a 32-bit constant. So this could have been like move LI, right? Long immediate or something like that. Okay? This is, again, a pseudo instruction. That's the syntax. You give me a register target and an immediate in any kind of representation you want. Here is a hexadecimal. You could put decimal, whatever you want to write textually. The tool will convert it to the equivalent binary representation in 32 bits. That's what it is. You can have signed numbers. It's going to be 2's complement. Okay. That's what it does. And this does not get translated into move high or I. Instead, they're using move high, add I. It's equivalent in terms of functionality, sorry, in terms of capability. It is not the same functionality, however. Things are done a little bit differently. Okay? And then we're going to see how this is done in a second. Yes, sir?
Is there an advantage over using aura versus add?
Honestly, this thing is bringing me like to tears in terms of excitement. I cannot see one. I can't. I don't know. Maybe I'm missing something, but honestly, I can't. I'm guessing it's for historical reasons. That's how MIPS did it in the first time. That's how they're doing it. Whatever you can do with one, you can do with the other. That's the bottom line. This is a bit more, it requires a little bit more attention from a human to get it done right. From a tool, who cares? And I'll explain in a second. A good point. I mean, I had the same question in the beginning. I kept thinking about that. At some point, I said, I have better things to do in my life. And I would suggest you approach it like that. At some point, if you have a lot of time, nothing to do, think about this for a couple of seconds. Okay. All right. So let's say we wanted to do this. Okay, just so we understand what the complications are. We wanted to do this with move high and add I. We want to move that constant to our 9. Okay. Now let's move to another favorite part of mine. How about you guys try this to do this? I'll give you 1 minute. Fair. Okay. It's not fair, but let me give you 1 minute to try this on a piece of paper. See what you can do. Now, in an ideal world, I will give you a lot of time. And then I'll ask each one of you, sit down with each one of you or not. Unfortunately, as I hope you understand, there are some practicalities here that we only have this amount of time. So what I plan to do right now, rather than asking each one of you and trying to facilitate some interaction, I will give you the answer, and then it's upon you to figure out how this fits with what you've done. So sorry for not looking at what you've done. This is not conducive to that kind of interaction right now. So it's not because I don't care. I'm not saying I do, I don't. I'm just saying it's not that, that's not the reason. There's not enough time. Okay. So long story short, I hope you got the message from the beginning. There was something tricky about this. That is, if you do it like this, you're not going to get the value you want. You're going to get something else. And now let's understand why. It all has to do with, with how this is interpreted by the machine. This is what you wrote. Remember, this is a hexadecimal number, and the reason we write it like that is because it's a convenient way to represent the particular bit pattern, which is all ones. However, the machine, as far as the add operation is concerned, is interpreting that as a number that's signed in 16 bits. And if it's all ones, I hope that you can remember, because the highest bit is 1, this is a negative number, and because all of them are ones now, this is actually -1. You with me? So the definition of the instruction says, whoever implemented this in hardware, they better first sign extended to 32 bits. That's what they're going to do. And if you do that, you see it messes up the upper part. So long story short, this is a slide that supposedly shows what's going on. So bullet by bullet, the first is the move high, 1000 in hexadecimal. That does what you expect it to do. It moves the bit pattern, which we specify the 16-bit pattern on the upper part. However, the problem starts here. That is, before, everybody okay with the first instruction? That's just the definition of the instruction. Second part, however, it says, this is the constant you gave me. We have agreed that this is a signed number. I have to add it now to 32-bit quantity, so I'm going to sign extended. So lo and behold, you end up with these thingies. And then when you add, you get this, which is not what you wanted. This is actually 0xff as opposed to 0x100 blah 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 blah. You with me? Okay. Is your life much better now? No. I mean, that's what the machine does. You just need to understand what it is. There's a very simple fix. I'll explain what it is in a second. First thing to realize is these are all constants. So at the time you're writing the code, you know what the constant is. You can change the constant to get the effect you want at the end. How can we do that? Well, the trick is this. The trick. What you got to do is the following. You say, if this guy, the second part, the 0xff, is going to be sign extended with all ones, and then it's going to be added to the constant that I'm going to have, which is 1,000, well, I need to somehow counteract the fact that it's going to be trying to subtract from it. So if you add a 1 just on the last bit, you're done. That's what it is. And I can show you, do I have the calculations to show you? I think I don't. But if you were to sit down and actually do that calculation, you're going to see that you will get the actual number you wanted, which is the 0x1000000. The best thing that I should have done to help you understand that is to write the numbers down so you can see it. I'll let you do that. What I have to offer you here is the following. You have to think, you can view the number as a 32-bit number, but you can view it as there's a lower part, a bunch of digits I don't care, and there's the upper part that's 16 digits. What's happening when you sign extend the lower number, you get -1 on the upper part. There are 16 bits up there. If you view it just from that part, if you think I'm doing addition 1 from right to left, I'm getting a -1 on the upper part. That's why if you add 1 on the 0x100, you counteract the -1 that comes after that. Okay, just do the calculation when you go home. Trust me on this. You're going to see what's going on. Any questions about this? I'll tell you about the two next lines underneath. So what's the rule? Long story short. If the immediate for the lower part has a bit, the highest bit is 1, well, you add 1 to the upper part. That's it. And then you have to sit down and understand why this is the case, but that's the rule. That's all there is to that. Will you ever have to do this by hand? No. That's the good news. But please understand there are these quirks. I mean, that's all there is to it. Why are we spending so much time on this? Because you have to deal with it because you have to program the machine. Also, it tells you have to be careful what the instructions mean and what they mean about your programs. The assembler will do that for you if you need to. So there are some macros now at the assembly level. If you have a constant that is 32 bits, you can use the % high at ADJ, which stands for adjust high end. And this returns a constant that's 16 bits that has the 16 bits of that, plus 1 if this has a bit 1 that's on the upper position, plus 0 otherwise. So it does the conversion for you. Okay, this is a macro. This is all happens at compile time. When you pass the assembly, you get the binary representation. And if you want to get the lower part, you just say % low. So this literally takes this part. This % low, this constant, is equivalent to writing 0xFFFF. That's it. It's just syntactic sugar. Any questions about this? Okay. Here, I mean, the % low seems like why would I do that? There are other facilities in the assembler. This could be a variable name, kind of a constant. So you can have a text over there that actually translates to 0xFFF. Okay. I hope I'm not confusing with this. Questions? Now, we've done version number 1, which was everything in the register. Version number 2, we want to move constants first to B and C, which are 16-bit immediates. And version number 3, which is we want to move constants into C and B that are 30-bit immediates. Everything was in registers. Remember, there are only 32 registers. It's not very useful. Besides, the registers are inside the machine. You haven't talked to the outside world at all. So now let's go to version number 2, where we're going to interact with the outside world. And our primary mechanism for doing that, we'll be talking through memory. Just looking ahead a little bit, this is parenthetic note. We're going to see later on in the course that the mechanism we're going to use to talk to devices will be exactly the same we use to talk to memory. For the time being, we're going to be talking to memory as a storage device. That's what we're going to use it because we're writing programs. But later on, we'll see devices that appear as part of memory, but when you write with them, you may be actually turning a light on or reading a keystroke from a keyboard. Okay. So that we all agree on what this thing means. On the upper part is the program I want to write. So there's a bunch of constants, A, B, C, and all of them are meant to be 32-bit. This is the statement I want to execute. And now we're going to assume that A is actually stored in this memory location. B is in this memory location, and C in this memory location. See, so these are addresses. Okay. And remember, I told you how I may draw memory sometimes. I draw it in this grid fashion. This is location, whatever is that, 200,000, 200,001, 2, 3 in hexadecimal. And then we go to 4, 5, 6, 7, 8, 9, 8. Okay. Everybody okay with this? I think I missed some number somewhere. 8, 9. It should be B, the last one. So this would have been 8, 9, AB. Okay. Good. Now, somebody came one day and put this data there. We don't care how that data went there. We just assume it's there for the time being. Later on, we'll talk about in the beginning there was nothing. You plug the thing in the wall. What happens inside the computer? And somehow, how do values appear on these memory locations? We're not there yet. Let's assume that these are there. Same thing as we did in the beginning for the registers. So the question is, how can we read B? How can we read C? And how can we read A? Forgot to tell you, who decides where the variables go? And again, in the interest of expediency, you decide where these things go. So in this case, I made a decision. I woke up one morning and I said that 200,000 looks like a good address for me for A, so on and so forth. Is the deep thinking that went into that? I guarantee you no. It's just, these are a bunch, it could have been any location, just pick those. So these specific numbers are not significant for the absolute values. They are significant once you decide what they mean. This means A, this means B, this means C. Okay. Second thing, notice that as a programmer, I wrote A, B, and C. And I know that these are meant to be 32-bit numbers. When I look at memory, this is just a sea of boxes with bytes and values in there. There is nothing in memory that tells you this is A, B, and C. This is interpretation. How do you interpret the program? And how do you write the instructions to manipulate these values accordingly? Nothing prevents from somebody going and saying, I'm going to go change this byte because I feel like it. Okay. Nothing prevents from a program from doing that. There's no mechanism in memory to prevent you, to force you to treat this as a 30-bit quantity all the time. There isn't. Okay. All right, so I think I spent enough time with logistics of this. Let's go to the actual instruction sequence. So remember, we want to do A equals B plus C. This will amount to read B into a register, read C into a register, add them there, and then write the result back to A. So it's a little bit longer process. Let me repeat that slowly. We're going to have 4 sections. Read B into a register, read C into a register, do the calculations inside registers, take the register result and ship it out to memory. So just from the get-go, there are 4 boxes we have to fill in. So if you wish high level, you've got to think read B, read C, add all of those. These are done in registers, and these are meant read into a register, and then take the result and write to A. Okay? So these are high-level boxes. My suggestion is when you do program at this level to think like that. I have this box to fill in. Who knows? It might be just one instruction. It might be 1 million. Who cares? I mean, that's the conceptually, that's what the box needs to do. You go and fill in the blanks. Okay? Now, what are the instructions we have in front of us? The first one is one that into a register creates a bit pattern that if I were to go and send it to memory and say read from that location, I will force it to read from location for B. So move A, as we said, is not an instruction, it's a pseudo instruction, it's a macro. Its end result will be R9 will take that bit pattern. So for us that are the programmer, we understand that this means this is the address of B. Again, there's nothing there that says this is an address, nothing inside the machine. The machine has no notion of this is an address. We know that because we are writing the program. Okay. Hence the name MOVA, because typically it's going to be used to create addresses. But it's a horrible name because you may use it to create a constant, which means something else to you. Okay. But that's the origin of the name as far as I understand. So far so good? So all we've done right now is in R9, we have a bit pattern, which if I were to send to memory as part of a load operation and say, please read from this location, I know I'm accessing from the beginning of A. Second thing I got to say to memory is the data type. How many bytes I want you to bring in. So this now is a NEOS instruction. Now, I hope this will not confuse you. This is not the operation that the memory does. This is the way NEOS will eventually go to memory and say, read do a load from this location. Unfortunately, it has exactly the same name. LD stands for load, and W stands for the data type, word. So this means Neos, please. Actually, it's not please. I mean, it does what you tell it to do. Neos, go to memory and say load 4 bytes starting from this location. That's what it happens. So at the physical level, this would trigger a sequence of actions. Eventually, if you're sitting in memory, you're going to see a load word for 4 bytes starting from that location. Everybody with me on this? Okay. So please understand that this is the way you tell Neos what to do, and then Neos actually does it. Okay. Unfortunately, in my notes and everything, I use load for both. This is the load instruction. That is the load operation at the hardware level. Right? This is the programmer's way of saying that. Okay. So what this will do is, now notice the syntax. It takes a register here. This is the destination register. Okay. When you talk to memory, you say, memory give me that value, and memory comes with the plate and says, here's the value. It's up to you to take it and put it somewhere, place it somewhere. This is where the Neos is going to place it. You're telling Neos, when you get those 4 bytes, put them into register R9. Okay. Now, how do you tell Neos to what address you want to access? This is called an addressing mode. That notation there is really take this constant, which happens to be 0, add it, or take that value from R9, which happens to be that number, add them together, don't change R9, just add them together. That is now a 32-bit quantity. Go to memory and read that. Should I draw this, or is everybody okay with this?
That's the address.
This is the address, but there's some flexibility there. Whether you like it or not, you have to use it. So when we say load word R9 0 R9, the steps here are the following. If this is R9, this says the following. Take this value, make a copy of it. Take this number, okay? This is, by the way, a 16-bit immediate. Sign extended to 32 bits. So now you have another 32-bit. This is another 32-bit. Add them together, and this is your address now. Okay. So it gives you this extra flexibility. So in our case, the number here is what we have over there. This happens to be 0. So it will get extended again to a nice 32-bit 0. It's a signed number, but 0 gets extended to 0. It will add them together. You'll get the same result as the address you're going to read. What memory is going to see, memory doesn't see any of that. Memory sees the final product, which is, this is the address, which happens to be exactly this value. Go there, give me 4 bytes. This is little endian. So what's going to happen is we're going to get 1, 1, 2, 2, 3, 3, 4, 4 being written inside to R9. Okay, questions about this?
What about load maybe hardware? So maybe the address that we have to get is from like 2 or
Yeah.
the multiple of 2.
Yeah, and that's valid. So you're right. One thing to remember, all accesses have to be aligned in use. We're lucky in this case because I wrote the program and I know what I'm doing, supposedly. So this happens to be 200,004. That's aligned by the size of 4. Okay, so that's okay. This is a legal operation. If it was 3, Neos will silently protest. Silently means it will crash your program. But you won't see any hand coming out and say, what are you doing here? Okay? So this is what's going to happen. We're going to get this. And then we're going to go to the location and get the result we want. Okay, so the slides are not very helpful to show you what's going to happen. But R9, after the load, will become 0x11223344. And I'm reading this in reverse because it's little endian. Are we okay with this? Okay. Now let's look at the full program in its full glory. I'll get back to those in 1 second. This is the full program now. The first 2 instructions, load B into R9. The second 2 I'm going to use the same instructions and correct myself. The second 2 instructions load C into R10. This does the actual calculation, and this stores into A. And I haven't talked about this guy, but it's the mirror of the load. I'll talk about this. Okay. Why did I say I will correct myself with the instructions? Because These are not instructions, these are pseudo instructions, and they actually get translated to 2 instructions underneath. Okay? So in total here, if you were to look at the machine code, there's going to be 1, 3, 4, 5, 7, 8, plus 2, 10 instructions in total. I hope I counted correctly.
For the loads, shouldn't the number or the register number in the brackets be like for the first
Typo,
R9?
yeah, typo.
Okay.
This is a typo.
Okay.
That's why you debug programs. You spend 10 hours then figuring what was wrong. Huh? Eh? He's right. This should have been R10.
Same with the one above.
Yeah.
Yeah.
I don't know how this survived all these years, and I should have fixed it at some point. Absolutely. And I wasn't testing you. This is a typo. Where were we? Where are you again? Why are we here? What's going on? You have a question? Come on.
Yeah,
No?
I was going to ask about that.
Okay, you got it. Okay. The universe still makes sense? Alrighty then. Now, let's talk about the store. Store is the reverse direction of the load. You're going to memory and you say, memory, I want to do a write now, a store. This is how many bytes I'm going to give you. Go to this location as calculated by this addressing mode and store the value that I'm giving from this register. Okay, it's exactly the mirror of a load. But for store, this is a source operand. You're giving this to memory. For the load, that is a destination because you're getting from memory. Giving data, getting data. Memory to do a load, the only thing it needs is starting address and data type. To do a store, that plus the actual data. Yes, please.
So for the last 2 lines, you moved that address into R11 and then stored that again in R8?
No.
Okay.
You're getting this address here.
Okay.
Then you're doing this wonderful process to calculate a final address, which in this case, because this happens to be 0, will be exactly this value.
Yeah.
Then you say, memory, here's 4 pieces of information. I want to do a store. I'm going to give you 4 bytes. Here are the 4 bytes. You read it from R8 and you say, here's 4 bytes. R8 serves as the place where you get the 4 bytes you're going to write, and you say, start writing from this location. Should I repeat that? We're good? Okay. And now we're going to do some optimizations. Because this is somewhat, okay, you know what? Sometimes if something works, you just move along. So this code, it just works. If you're not going to be executing this forever and ever, it doesn't take a lot of time, maybe you want to leave it alone and move to something better. But if it's going to be something where you're going to spend a lot of time, it's like a performance critical loop, maybe you want to reduce the number of instructions. So let's see how we can do that. I'll give you a hint. The hint here is that if you look at this, you do have immediate here. Right? So you have control of what value you're going to place there. And by the way, you do know the relative position of all variables in memory. What I'm trying to say here is this, blah, 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 blah. If I were to say, you know, I have a spot in memory, which happens to be 200,000. A distance 4 from it, notice the term I used, distance 4 is B, and a distance plus 8 is C. And you can pick any origin point you want in memory, and you can express everything relative to that. So that distance, I want you to understand that as a number of steps. I can say, look, I'm in this spot in this room. I'll make 4 steps, 1, 2, 3, 4. That's the 4, right? The origin was there. I can adjust my origin, and then the offset remains the same. So as long as you make sure that these variables are allocated one after the other in memory, you always know that A is at the origin point, B is a distance 4 from the origin point, and C is a distance 8 from the origin point. How is that useful to us? Well, let's go to the code now. This is the original code. And now, this is the code where I use an origin point, which is the beginning where A is. So notice that these are no longer zeros. These are 4 and 8. Why? Because B is a distance 4 from A, and C is a distance 8. How can I do that? Because it's my program. I place them in memory. I decide to put them there. When you compile a C program, the compiler does those allocations for you. You don't have to worry about that. You declare your variables in your text, and then the compiler does this allocation for you, goes and sets those. It's actually a bit more complicated than the sequence of tools. At some point, if I have time, I can explain to you how it's done. Unfortunately, today with all of these development environments, it's all graphical. You press a button and all these things happen underneath, so you don't necessarily see it. In the good old days, you had to do everything by hand, which was really ugly. Okay, but it still happens the same way underneath, it's just automated. So far, so good? Everybody okay with this? Questions? Okay. So a standard trick in NEOS and MIPS and all these machines is to put a pointer somewhere in memory. And then all global variables, that is variables in C which you declare outside of functions, as long as they fit in that space, you declare, you put the pointer somewhere there and you access them, all of them with as an offset from that. There's a specific register which by convention is used, it's called global pointer. You can look at the manual which it is, but you don't need to know that, it's just other information.
So that should be also wherever you have like the 4, 8, and the 0, that should be R9 this time, right?
Oh, you mean the typo?
Yeah.
At least I'm consistent in my typos.
At the top. It should be move IA R11 2000. That'll make
Yes,
everything else.
yeah, he's right.
Okay, so the only one at the top.
So let's fix this so that everybody's on board, okay? Otherwise, this is going to be a mess. This code is incorrect as it stands. I believe, and you guys are ahead of me, so you can double check this. I think this is the correct code. What I fixed was I went and made this R11. Otherwise, we have a problem because the first instruction actually overrides R9. Okay. So create a pointer to memory to location 200,000. Everybody refers to that relative to that. Any other thing we can do? Yeah, minor thing now. Notice that the first value we're creating, we're using move EA, which is a 2 instruction sequence, but the lower part is all 4 zeros, right? So we don't really need move EA. We can just be clever if we want and do this. We can say just move high R9, the upper part. Why? Because we know that this is going to zero out the lower parts, and we know that because we can reason about that as humans. Does that make sense to you? These are equivalent because of the constant, the specific one.
The previous slide, is it the same typo for both?
Yeah.
Like if you go back when it's R11 for the first time?
Yes, it is. Yes, this is a, sorry, this is a mess. I just didn't fix it on this slide.
Okay.
I'm just doing this. These are pre-made slides. And this is what happens when you do things and you're thinking other stuff. Okay. Now, commentary now. This, I feel very proud of this optimization. Is this a good idea? It depends, because it makes your code harder to read. So again, this is a trivial example. I'm not going to argue with you whether it's a good example or not. I'm just using that as an opportunity to raise a point. Sometimes it's better to write inefficient code so that later on you have a chance of actually reading and understand what it does. Only if something is really performance critical, you go and you beat it to death to extract every tiny bit of performance out of it. Otherwise, readability is the most important thing, because I guarantee you, I can guarantee you myself, 5 minutes later on, I won't remember what I was doing. Most people, a month later, you won't even remember what this thing is doing. So don't do these optimizations unless you absolutely have to. Most of the time, you just press a button, you let the compiler do whatever it wants, and compilers are pretty sophisticated these days. They do a very good job. It's only on really, really performance critical loops that it matters. Like if you have like 4K video you want to decode or whatever, there's like a tiny loop inside. That maybe you want to hand code it. Other than that, compiler is going to do a pretty good job. Okay. Now, let's talk a little bit about, we have 10 minutes left. And there is 2 topics I want to touch. Let's go to this first, and then I'll go to the textual representation, how you're going to write this in assembly. So somebody was talking about I don't remember who was, just a second ago. See, no memory whatsoever. So the load word, store word we saw are just one set of load operations. There's a bunch of others that have to do with shorter data types. Load word and store word, there's only one load and one store because it's the maximum data type. For everything else, there are 2 loads. Okay. So, for example, there is load half word. Load half word means go to memory, get 2 bytes. The container you're writing to the destination is always a register. The register always has 4 bytes. So regardless how many you got from memory, you got to fill in 4 boxes. That's why there are 2 varieties. There's load high, which means signed, and load high U, which means unsigned. This one fills the upper two boxes inside the register with zeros. The other one takes the bit 16 of what you got, the 16th bit, and replicates it. So either makes everything 1 or everything 0, sign extension, okay? This is 2 bytes, equivalent for 1 byte. So for example, if we were to say, with this particular case, right, if we were to say, load half word R whatever, R8, 0 R9, where R9 happens to be move VA, R9, 0x, 200,000 of 4, okay? This will go to this location. From memory, you're going to get 2 boxes, which is starting to 200,004. You're going to get the boxes 3344. So you're going to get this number from memory. And then inside R8, you're going to get 44330000, and this is in hexadecimal. Everything is binary inside the register, okay? Everybody okay with this? That's what's going to happen. We go from 200,004, we get 2 bytes. This is what memory gives us. We sign extend this to 32 bits, because if I were to write this down, it's this number. This is the sign bit, zeros.
Can you write that a bit to the left, like that last number?
Yeah, this is, I was just writing this hexadecimal into this form. I understand, sorry for that. Now, if we're following, however, load high R8. And let's pick a nice constant here. Let's pick this guy. So 4. Okay, what's going to happen is this. This is the value in R9, which is 200,004, plus 4, 200,008. This example is not very good. Yeah, because this is what's going to happen. I wish I had different numbers. We're going to get the following, 0x7788, and then that's going to get translated into R8 again as this. Sorry, you won't be able to see there. 00007788. So that's not a very good example, but I'll do it with a byte in a second. Okay, everybody okay with this? Is that a sign of desperation in your eyes, or you're okay? Yes for the first one, or yes for the second one? Okay, thank you. Thank you for being kind with me. Now let's do one final example that hopefully is going to illustrate the point. Where is my favorite thingy? Yes, this is the favorite thingy. So, ta-da. Let's do load byte R8 for R9. All right, now I'm very happy with myself. This is going to go to location 200,008, right? From memory, we're going to get this number. Notice I said byte, okay? What's going to happen now is this is going to be expanded, sign extended, and what you're going to get in R8 though now is this. 88. Okay, why? Because if you were to write this in binary, it's 100100. They brought pizza? Coffee? Can get delivery. Okay, good. Everyone okay with this? Now we can keep doing examples, and I think you should. Okay, this is a point that's, if you're going to make a mistake on this, it's going to be a trivial mistake. There's no way to do a complicated mistake here. It's going to be trivial. So you can mess this up. I mess it up sometimes as well. Never do mistakes myself anyway. And but so please work on it. There is a bunch of examples in the notes. Try to work around them, because this is a point of confusion. Okay.
If we did load BU instead of B, then we all zero.
Load BU, same thing, will give you this. Because it says treat this as unsigned. I don't care.
Load B or load H would only take the lowest of the 4 bits, the lowest least significant byte, right?
Say that again?
Load B would only take the least significant byte, right? How would you
Load B, here's the thing. I think there may be a confusion here, and I may have not done a very good job. Every load gives you a point of origin in memory. The data type is how many bytes to get after that. When you have byte, there's only one byte. There's no question of least significant, most significant. It's just one. The question of little endian, big endian becomes relevant only when you have data types for more than 1 byte. So for half word, when you give me an origin and 2 bytes, I'm getting the least significant one to be my most significant when I write in the register.
So for load byte, you can give a non-multiple of 4 address?
You can give any address.
Any address.
For load half, it has to be divisible by 2. So if you were to look at the address in binary form, the last bit must always be 0. That's in binary, that's what it means is divisible by 2. If it's a load word, the load 2 bits must be 0 because it has to be a number that's divisible by 4. And that's how it pans out in binary.
And byte
Okay?
can be anything.
And byte can be anything because exactly it's byte, 1 box, that's it. Okay. I still have 5 minutes. Okay. Will you? It's mine. Give me my 5 minutes. Okay, now, some practicalities now. How are you going to write all these wonderful things? You're going to work with very, very powerful tools, which is basically a text editor, and you're going to be clunking in characters. That's what it is. This is assembly. Normally, what your C compiler or your Java compiler, all this kind of stuff, this is the output. That's what they spill out. When you write a C program, the C compiler spits out assembly, and then there's other tools that convert this to machine code. So now we're throwing out the C compilers, we become the C compilers ourselves. You have to write everything by hand. So this is the notation. Now, notice that there are essentially 2 parts to this. One that looks like code, and another part that looks like data. Let's look about the easiest part first, the code. The code is what we described before. It's a textual representation of what I was writing in my slides. That's exactly what it is. What signifies something as code is this thing. If you say dot text, this means it's something you're supposed to read to the machine. It's all read only. These are the instructions. So anything you write there is supposed to be interpreted as machine instructions. Dot data now is supposed to be data. So you're not putting instructions there. You're going to be using some other notation, which is again for humans. It's not. This doesn't exist inside the machine. So that when the program gets loaded in memory, before the program starts executing, those values will appear at their specific locations. Okay. Notice, unfortunately, you have no control at this level where this starts at and where that starts at. Okay. So I want you to have the following mental picture to understand what's going to happen. Yeah.
Before we erase that so earlier you go
Sorry.
B,
Yeah.
right? So that's loading a byte,
Mm-hmm.
and the byte is 4 bits.
No, 8
8, okay.
by convention.
Alright.
Byte always means 8.
Okay, and half is 2 bytes.
2 bytes. Everything is bytes. There's no manipulation of bits here. When you go to memory, memory always responds. The minimum quantity you can ask memory for is 1 byte. That's the minimum. And the maximum you can ask is 4 in this machine. Okay.
So 1 hexadecimal is half the byte.
Yes. So, and I'm not going to be writing all of them all the time. I just, again, there's context sometimes. Okay. But feel free to ask every single time so we make sure we're on the same page. And don't trust me when I write things. Double check me because I don't trust myself. Good thing is nobody's going to die if I make a mistake on the board. Okay. Where were we? Okay, so mental picture. The way to understand what's going on is the following. What happens when you pass your assembly through the tool is creating an image of how memory should look like before your program executes. There are other mechanisms then before you actually hit run on your actual board where that image is being created in memory and your program runs. This is the equivalent of an operating system. If you go to Windows or Linux and you type a command or you click a button, what happens is the operating system goes from your disk, gets a copy of what that program is supposed to be before it starts. It makes an image of that in memory. That's the operating system does that for you, and then starts executing it. Okay, we can talk about these details later on. For the time being, just assume this is done. So now let's understand how you're creating the image. So there is memory, which as we said starts from location 0x and it goes up to location 0xFFFFFF. By convention now, the tool that does the mapping maintains 2 pointers into that. The first pointer is the pointer to the .text. These are called segments, but this is just words that people use to refer to the portion where I'm assigning instructions. And there's another pointer, which is to location.data. Now, if you care to find out how to set these pointers, you have to learn about linkers and how they set them up. The particular toolchain we're using is a very popular toolchain. It's called GNU, whatever is a foundation, whatever. They have their own, you have to find some obscure configuration files to set those. If I remember correctly, this is, but I may not, this may be a location 10,000 or 100,000, and this may be a location 200,000. These are just two numbers I'm putting up there. Don't assume that's what they are. There is some configuration file that these are set, preset for you. You don't control them from the assembly. There is a completely different configuration file where you get it. So these are implied. As your assembler parses the text you're writing, it's actually text, but sorry, the file you have written, at any point, it knows whether it's inside a .text segment or a .data. What it does, anytime it finds a statement that will spill out data, it just places them at the last point where it stopped in that segment. So in the beginning of time, both of them were empty. So I'm parsing that file. It says I'm doing .data. So the assembler thinks now, okay, whatever I will find that actually I have to place, I will place into the .data segment over here. So it finds a line 2. I'll explain in a second what that means. Let's forget about that. It's a directive. Next thing it says .word 0. That word means what? What comes after that is a constant, some representation of a number. I want you, assembler, to convert that into 32 bits and go write it to the next memory location where your .data segment is right now. So that's going to go into the .data segment here, data. It will allocate 4 bytes one after the other. Let's pretend this was 200,000. So now that data is going to point to 200,004 because we just finished with 4 bytes. And then it will make all of these zeros. These are going to be a lot of zeros because that's what you said. It's a constant. Next thing is that is going to create another 4 bytes in memory, which if you were to read as a word hexadecimal, in hexadecimal form, it would be 44332211. It's a little endian, that's why it's written like that. And it puts that in the image that's supposed to be. And then the pointer is going to be 200,008. So far so good? Everybody understands what happens? And then C is going to go underneath. When you hit the text, it goes in this and starts putting the machine code instructions. If there was another data statement under here, when you do something, it will switch to that and keep adding to that. That's how it works. Final thing I think now we need to get out. And I will clarify that in a second. And we'll do it 2 days from now again. Notice that there is A colon, B colon, C colon. These are syntactic sugar. These are labels. From this point on, anytime you use the letter A in any context other than the machine code instruction is equivalent to the number 200,000. Why? Because this is where the data pointer was at the time you created that space. From this point on, the origin of that, what follows is 200,000. B is going to be 200,004, and the other one is going to be 200,008. You have a question?
Yeah. So what is the dot line?
Data line means wherever you are right now, whatever pointer you have, make sure you go to the next location or stay there that's divisible by 4. So 2 is the power of 2. It says make sure whatever you put after that, it starts at the location that's divisible by 4. Here, this starts by 4. If this was 200,001, it will go to location 200,004. It's a directive to the assembler that says, I don't know what you've done so far. Make sure that the next location is divisible by that power of 2. Okay, good.